Hi, this is Mr. Yeager again, and we are now looking at free body diagrams this particular time. So here we go. Last time we were looking at all different forces. This time, this is the most popular way in terms of how we will try to organize all of those forces and illustrate what an object might actually be doing. So let's get this started. All right, so we already talked about what is net force, okay? And a net force is, again, when there's zero, when all the forces acting on the object are the same. That's what we're basically looking at here, right? And so this already shows you basically a basic free body diagram, and I'm going to go over the main ideas here. On a free body diagram, what you basically need to see is we're going to draw every object out there basically as a box, okay? If I say it's a car going up a hill, we're going to draw that as a box. If I say it's a cat falling through the air, that would be a box. If I say it's a person, the person becomes a box. So it doesn't matter what the object is, we draw the object as simply a box, okay? A nice little square. And then on that box, we're going to draw the different forces. And all the forces, as you can see, always point coming from the object. All right? They always point coming from the object, never pointing at the object. Because we're interested in what forces are acting on this particular object. Well, weight is pulling it down, normal force is pushing it up. So that's how we always draw these free body diagrams. Never, ever draw the force going at the free body diagram or at the object at the box. Okay? That's what we're always going to be working with every single time. So don't overthink the process. Just go, okay, what's acting on it? Okay? And draw it as a box. All right? The forces that we'll obviously be using, okay, basically all the ones you can see here. Okay? We have contact, action at a distance forces we call field forces. Okay? Any of these could pop up in any question. You know, don't be scared. Don't be sitting there going, oh, you didn't talk about electrical. How do I show electrical? How about FE? Sounds good to me. Okay? So just write out anything that makes sense for that particular force acting on it. All right? The most common ones you can see are these right here. Okay? These would be the main ones we're going to be using quite a bit. Again, like you saw me do in the last PowerPoint, in the last video, this could be N, this could be little f, all right, this could be F of A, this can be W, and so forth. Okay? Do not overthink the symbols, please. All right? So that's what this is saying. There's no standard for the abbreviations. Just move forward. All right? So we already talked about a lot of these forces. I think I can skip some of this. Again, a normal force always will point perpendicular from the surface. A frictional force will always point parallel. Okay? So, from there we're going to start drawing these free body diagrams. And again, you can see the other example right here. Okay? Again, the arrows are meant to show you the magnitude and direction of the force. Force is a vector. We didn't specifically say it before. Force is a vector quantity. It has magnitude and direction. I usually do not get into too much detail sitting there going, you have to draw this the exact amount compared to the applied. It's not going to be a big deal. If the applied is double the frictional force, I don't care if they both look exactly the same. Okay? That's not going to be asked for in this class at all. But the thing is, you might see some pictures where the applied force is clearly longer. Oops, just moved my own picture there. It's clearly longer and probably means that it is larger. But don't always worry about that too much. Okay? So this one's showing you that you have 4 forces acting on it. There's no rule. That's all this one's saying. Put as many forces on the object as you want. Okay? There could be 1, 2, 3, 4. There could be 0. If it's in the middle of outer space, there's no forces acting on it. So here we go. Let's try a couple problems together. A book is at rest on a table. Okay? Diagram the forces acting on the book. Okay? So, all right, this would basically be your answer. What forces would be acting on the book? It's sitting on a table. I sometimes like to draw a surface. So if you want to draw a surface out, do it. That's not going to be marked off. Okay? But the only forces acting on it would be weight down, normal up. Weight always, always, always points down, regardless of the situation. Okay? Moving pretty quickly. That's basically the same thing we just did at the very beginning. Same exact free body diagram. All right, let's look at this one. Let's actually write this out. An egg is free falling from a nest in a tree. Neglect air resistance. Draw the free body diagram. Okay, so an egg is falling from a tree. What would be acting on it? Well, we know weight would be acting on it. This egg's falling down. Okay. Is there any air pushing it back up? No. It says neglect air resistance. So guess what? How many forces are acting on this particular object? It's going to be just one. Ta-da. That's it. And that's a perfectly good answer. Don't go any farther than that. There's another one. A flying squirrel is gliding from a tree to the ground at a constant velocity. Again, don't overthink this. Let's just assume the flying squirrel is going straight down, but just falling slower. Okay? Now this one is saying, consider air resistance. What would the free body diagram be? That means I must have weight, which points which way always? Down. And air resistance, I'm going to say F of air, which obviously is trying to slow it down, so it would be pointing up. That's all we're looking at, these two forces. Let's see if we got the right answer. Oh my gosh, we do. Okay? Do we care that, are we asked whether they're equal to each other? I mean, we actually could figure that out. It's moving at a constant velocity. Woohoo. Those are key words throughout this unit. Pay attention to those. If I'm moving at constant velocity, that means we're at equilibrium. Forces are equal. All right. Problem 4. Take a moment to look at it. A rightward force is applied to a book in order to move it across the desk. Consider frictional forces, neglect air resistance, construct a free body diagram. Okay, so what do we have here? We have a book. Okay, there is a rightward force applied, so we have a force applied. It says there is friction, so it must be going in the opposite direction it's moving. What else is acting on the book? Well, it's on Earth, so we got weight. And it's on a flat surface, so we got normal. Put all of those together. All of them together. There you go. All right. Problem 5. A skydiver is descending with a constant velocity. Consider air resistance. What does this sound like? It's the flying squirrel problem again. There you go. Weight down, air resistance up. Weight's obviously always going to be involved. You immediately know what force is on it. Weight. It's on Earth. So draw one force going down all the time. A man drags a sled across loosely packed snow with a rightward acceleration. Draw the free body diagram. Okay. So what do we got here? It's probably the same thing as when we pushed the book across the surface or whatever that object was. All right. So the person is dragging the sled to the right. We could probably say it's either tension, maybe he's holding a rope, or F applied. There'll be weight, there'll be normal, there'll be friction. It says consider friction, so we got to hold on to that. Okay. There you go. Maybe not as much friction, but there you go. All right. All right, so going over net force just very briefly, what we're looking at here a little bit is just how to add up forces and so forth. When do we add? When do we subtract? All right. We talked about how the formula is net force equals m times a, Newton's second law, which equals sum of forces. All right. The thing is, what this is basically saying is we will add up forces if they're going in the same direction. We'll subtract forces if they're pointing opposite. All right. And the last thing is vertical and horizontal forces don't match up, just like in projectiles. Don't forget, we never put a vertical velocity into a horizontal distance problem. Vertical and horizontal components are separate. Okay? So, if I look at a problem, okay? If I have this particular problem, there's a tension of 1,200 newtons up and a weight of 800 newtons down. That means there's going to be a net force going up of 400 newtons. Now, net force is never drawn on a free body diagram. That's because it's not a real force. It's just how much force does the object end up actually feeling that will affect its motion. All right? So net force is never drawn. Don't ever include that one. All right? But you can see what we did. We subtracted the two forces. They were opposite to each other. All right? Okay? Look at this example. Okay? What would be the net force of the object down at the bottom here? What would we do here? Would we just add up all three forces? No. Okay? We only will add and subtract forces that are in a vertical direction together or horizontal. And so what we see here is I have a 50 Newton force up and a 50 Newton force down. So what am I going to do with those two? Subtract. So what's my net force vertically? The net force vertically, which I can call F net Y, would be 0 newtons. But let's look at it horizontally. Horizontally, I have a net force of 20 newtons pointing which way? To the left. So there's a net force 20 newtons to the left there. All right. So again, just pay attention to the directions of the forces, of the vectors. If they're together, you add. If they're not, you subtract. If they're vertical and horizontal, don't mess with them. Okay? You can see I don't even have any right there. Okay? If I said you had a force going up of, you can't see that. If you see it going up with 5 newtons and to the right with 5 newtons, you can't add these. Okay? Don't add. Don't add or subtract. We can't do anything with those. Actually, we can create a resultant, but we'll talk about that another day. Okay? And that's basically it. So free body diagram. Every object is a box. Identify the forces acting on it. Draw it appropriately. And that is basically your big homework for this weekend. All right? Perfect.